So welcome to the lecture number 8 for the MOOC on peer-to-peer networks. So in the previous lecture, I had covered about Pastry, and I have shown you an example that if we just depend on routing table exchanges, then our routing table may not converge correctly. So one of the important mechanisms in CORD was use of predecessor and successor both. We can also call it leaf set. Pastry actually terms it as a leaf set. And with that, we were able to always lead to the correct routing table. So convergence was always guaranteed. So that's what we had discussed in the previous lecture. But there was a problem in the CORD that the node IDs are just being randomly picked up by each node. So maybe your neighborhood node, when you are forwarding a query or when you are trying to publish a key value pair, might be going to some node which may be all the far off. He may be just the opposite direction on the earth actually. So if you are in India, the other node, next neighboring node might be United States. And then maybe the next node may be again back to India. So the proximity is not guaranteed. This basically in the node ID space only we are looking at closeness. And based on that, every time the query or the key value or hash ID for the key is moving towards a node which is closer in node ID space, but it is not taking the optimal path. So this was one of the problems, and so this need to be resolved. So that's why the Pastry actually got invented. So we will be now today looking at the Pastry, which is another DHT routing algorithm, and which is has technically is very similar to CORD, where the root nodes are defined, except the minor changes in the definition of distance. We will be revising the CORD first, and then we will move on to Pastry. So just a quick revision of CORD. So CORD, in this case, the all nodes are maintained, at least has to maintain a predecessor as well as successor node. And all nodes are supposed to be arranged in a circular fashion, as you can see in the figure. So they are arranged in a circular fashion. Okay. So this will basically depend on the node ID. So if this number is going to be 0, this has to be something which is higher than 0. So there is no other node which should exist between these two node IDs. They are all arranged in a circular fashion. So you start from 0, go all the way to 2 to the power n minus 1. If there are n bits which are contained in the node ID. Okay, and we are using modulo numbering. So we essentially, in this case, once the numbers get actually finished off, we again go back to 0. So this circular arrangement is maintained. And in CORD, normally we have a mechanism by which if the hash ID will be lying somewhere on the circle, and whichever node ID is going to be immediately after that in a clockwise direction, so that will be the first node, that will become the root node. So I will explain the actual definition of root node. We had discussed this thing earlier also. So this is the way it is going to be arranged. So I am taking an example of 16 node ID space. So numbers can be only given from 0 to 15. So there are some nodes. So when they will be arranged in the circle, so one after that the 5 will come. So there is no node which is going to have a value 2, 3, 4. So then only this can happen. And from 5 there will be 9. So remember they are in order. So you are not going to get a 10 here in this position. So you won't get 10 here. Okay, if you want, you won't get 10 here. So 10 has to be only after this. So 10 can only come at this location. So this cannot come here. So this is going to be the correct if I have to insert 10. Okay. So this is the way the things are organized. Now the hash ID or the key value. So basically there will be a key and you will be generating hash function of hash of the key. This is what will be your hash ID. So this hash ID is what is going to be, for example, the hash ID belongs to this particular point in this node ID space. Then root node for this one will actually be 0 in this fashion. So this basically the definition is the node ID which is closest or which is greater than or equal to the hash ID and which is smallest in magnitude in cyclic fashion. So that will be the root node as per this definition. So if at any point of time you actually have your hash IDs in this range, so then this will be the root node. So this is how it is going to be happening. We can actually take this and define this as in a mathematical form. So as a distance metric, this we had also discussed in one of our earlier lectures. So from a point I, so from you take a point I here and to a point J, if you want to find out a distance, and this distance has to be taken in this fashion. Okay. So this distance will be given by J minus I, and this can also be negative, need not be always positive, because after 15, it's the circle is completing and I am coming back to 0, 1 and so on. So J minus I can also be negative. That's why we can add 2 raised power n. So basically, and then do a modulo operation. So that will give me the distance always in clockwise fashion. Okay. So for a hash ID I, the root node will be any node whose node ID is j such that dij is the least. So you have to choose j such that dij is minimum for a given hash ID. That node j will be the root node. So that what will be the definition. So typically how the routing table will be there. So routing table at each node is called finger tables in case of CORD. This we had also earlier discussed. And normally if this is the current node I, so every node should maintain a successor and predecessor. Immediately any node which is smallest in number but is higher than I, that has to be retained in cyclic fashion, and a predecessor, the previous one. These two always have to be maintained. And after that you can actually find out the root of halfway across. So total number of node IDs are 2 raised power n. So this 2 raised power n divided by 2, 2 raised power n minus 1. So this actually will, when I add to I, this will point to diametrically opposite point. So whatever is the root node of this, so this will be the root node if there is no node exists in this range. Okay. So this will be kept in the table. So in the finger table. Similarly for the quarter, 2 raised power n by minus 2, I will add to I and find out what is the root node for this. We will keep all the entries. So ultimately at 2 raised power 0, I plus 1. So root node of I plus 1 will always be successor. So predecessor is always kept for the optimization purpose. Otherwise you won't be able to you can't stabilize the routing tables to the correct entries, as we had seen in the previous lecture. And of course, now the routing strategy is very simple. For hash ID L, so L is a hash ID which you want to find out. And there are many nodes which are going to present. For example, this I contains this node, this and this 3 nodes. It will choose a node such that from the hash value. Okay, we have to choose a node such that from the node which are listed in my finger table, from that node to the hash ID, the distance should be minimum. Okay, so once that is there, so for example, the hash ID is suppose at this position. So this is the hash ID. So in this case, I should now hand over the query to this particular node. So this node now will further find out if its successor is immediately after this node, after this hash ID. So successor should be the root node. It will then inform the successor that you are the root node and this is the hash ID. Then it will actually look into its own database. So in fact, every time you trying to minimize, you are choosing case such that DKL is the minimum thing and handing it over. At some point, the node will figure out that it is the closest guy. Okay. And then that guy will figure out the successor and hand over the query to him and tell him that you are the root node. That is to be told to him specifically. Otherwise, he will look at his own finger table and he will find out somebody else who is closer to that hash ID. So routing has to stop here. And this guy will then has to specifically ask him to supply the key value pair from his database. We can modify this definition slightly and make it simpler. I will do that later. Now regarding these pointers, there is always, for example, I am pointing here. This is same thing which I had mentioned in the previous recorded lecture. that this is pointing here. So if there is a better pointer from in predecessor and successor, somebody is more closer to the halfway across entry. So halfway across entry, for example, is pointing to somewhere here. So then, and it is now pointing here. So predecessor is at this point, successor is here. So this remains the root node. But if my halfway entry is pointing here, okay, so this is going to be, this is I, so this is I plus 2 raised power n minus 1. And the finger table contains this node's entry. So whenever this node is going to send back the information about predecessor and successor, this node will figure out the better entry is this, so it will change the pointer to, instead of this, the pointer will be modified from here to here. So this entry will no more be valid. Okay. So this how actually you keep on optimizing the pointers in the finger table. So this predecessor successor actually does that job. So this we had discussed earlier also. So once the current node I will satisfy the DIL, where L is the hash ID which we are searching. This is the hash ID. This is what we had used in the earlier slide. Is the least value. The successor of I will be the root node. This is what I mentioned earlier. Now we can actually avoid this specific condition if we choose my root node definition slightly differently. So we can actually choose that root node, a node k such that DKL. Remember earlier when the root node was being defined, it was DLK. So we were choosing k such that DLK gets minimized. But now we are not doing this, we are doing this one. So node k is chosen such that DKL is the least for the hash ID L. So that k will be the root node. Okay, so in this case, if this is the range of hash IDs, the root node will be the previous guy, predecessor to each one of the, this hash value, the predecessor is this, so this will be the root node. Okay, now this is a relative logarithmic routing. Now when I want to, in this case only numeric ID based search can only happen. I cannot actually choose based on geometric or actual distances which are closer to me. I need something different. So that's what the Pastry did actually. And of course, I had already talked about the finger table management, and this was also part of the previous lecture. Now we are going to use still this Pastry. This algorithm is trying to use the proximity metric, or the actual distances also will be accounted for. But the root node definition or the node ID space, the distance metric is still based on the circularly arranged nodes. So that's a key thing. This is same thing as what happens in the chord. Okay, and so still arrangement is circular, and two neighboring nodes may actually be far off in case of chord, even in terms of round trip time or hops or geographical distance. And this cannot be done in chord, so but Pastry can do it, as I mentioned earlier. So let's see how it does actually. So first of all, what is the root node definition in the chord, in the Pastry? So if there is a node is lying here, so next successor is here, predecessor is here. So halfway across we will divide, and this for this whole range, this node will be the responsible node or called the root node for this range. So it's a absolute distance which is going to be important here. So technically your Dij will be given by minimum of I minus j plus 2 raised power n mod 2n, or so this is what is going to be the distance metric now. So the node which is closest to the hash ID, that will be the root node in this sense. So this distance represents this. So I am actually going either this way or going the other way around. Either way, whatever be the distance. So I to j or j to I, both I am actually taking. So this will be the root node. But there can be a problem actually, that a node, your hash ID may be exactly in between the two nodes. In this case, who will be the one? So both are actually equidistant. So in that case, you can actually decide to choose the next higher entry all the time. So, but it has to be consistently done with everybody. Otherwise, you won't be able to find out the root node. Root node has to be unique in the system. So each node in Pastry will maintain 3 tables. One is called leaf set. So this is an extension of just maintaining predecessor and successor in chord. This is basically extension for that. Routing table is now slightly different here. It's not based on finger tables. And there is one third thing, which is neighbor tables, which essentially now look into take care of these three distances which were mentioned here. These three distances are being taken care of. So it can be chosen by any one of them. So, but that is being left to the implementation of the algorithm. So the leaf set, first of all, let's define what the leaf set is. So its size will be given by some parameter L. I will tell you what the L will be actually. So L by 2 nodes which are higher and closest to the current node, those will be the part of the leaf set higher side. And there is a leaf set lower side which is L by 2 lower nodes, but which are closest to this current node. So this set of, for example, add node 8 nodes will form a leaf set. So where L is now 8 in this case, so 4, 4. So that's what the leaf set, every node is supposed to maintain it. So even if some node dies off, so this guy will be always exchanging leaf sets with all the members of the leaf set. So its leaf set will be given to this person. So this will be giving the leaf set to him. This guy will be communicating leaf set back to him. So in case if some node dies off, so they can always repair it and always maintain 8 nodes in their leaf set. So basic principle is ask the leaf sets from all the nodes in your leaf set and choose the best option to update your leaf set. So that's going to be the key rule, which is maintained by all the nodes. So all the nodes will keep on maintaining the leaf sets accordingly. And whatever node you choose, you start taking leaf set, ultimately you will end up in building up your own optimum leaf set and you will stabilize onto that. So all the nodes which are being reported, you normally do if you are doing a ping based proximity closeness, it's basically based on node ID. There is no ping test here has to be done. It's based on node ID. So it's a very simple algorithm in this case. The similar thing is also done in case of neighbor table, but that's where we are going to use a metric which is defined by one of these three, or maybe something else, whatever the application developer decides. Okay. So in fact, if you note down that the same principle we were using, so leaf set L value was 2 in case of a chord. So in this case, the value of L need not be always 2. It can be higher, it can be 4, it can be 8, it can be 16 or 32, whatever as an application developer you decide. Okay. And of course, another important thing, even the entries which are received when the routing tables are being sent by other nodes or the neighbor tables are sent from other nodes, even those entries are also considered to make a better choice for your leaf set. So this is an ongoing process all the time. Leaf set, normally this will not be required, but you should always consider all the new information which is arriving at you for a faster convergence. Now when a hash ID is to be routed, so how routing has to be done? So routing here is slightly tricky. So you are always going to do the, first of all, use the routing table. And once you reach here and you find out you are the closest node, you will start using your leaf set for doing the routing. So if you get a hash ID, this guy gets the hash ID, which is at this point, and there is no more closer node. This is the only closest node as per the routing table. I will talk about what the closeness is. Then you start looking at your leaf set. So it finds out this guy is actually in between these two. So whichever, it will just hand it over to one of them, or it will basically find out which one is closer. If both of them are equal, it will give to the higher one as per the consistent rule. I have been following the node which is higher, or this node one, if that is whichever is closest, that will be picked up and entry will be passed on to that. That guy will again look at his own leaf set and will find out he is the closest node, so he will look into database for the corresponding key value pair, or either he will publish depending on whether it's a query message or it's a publish message. Now coming to the routing table, how the routing table is built. So for fast routing table has to be maintained, because in fact you don't need a routing table. You can actually work without a routing table, because you can keep on passing through these leaf sets, but every time you can jump at most by 4. So you can do 4 jumps. So if there are n nodes away, you have to go. So if the total n by 2 nodes are there halfway across, if they are uniformly distributed, so n by 8, roughly those many hops will be required to reach to your root node in worst case scenario. Okay, so that is not desirable typically when n is very large. So you would like to go into log n steps instead of steps which is some constant into n. So for this, the routing table is maintained. This is going to be pretty fast. So in case of n, if it is the size of node ID space, so n, for example, is 2 raised power 256. So 256 bits can be used to represent a node ID. The number of digits which will be required will be log 2b raised power n, where 2b, b is the number which we have to define. So this is base 2b digit has to be used for representing the node IDs. So I can use that. So 2b can be 3, it can be 4. Normally b is equal to 4 is used, but in our example, we'll be actually going to take b is equal to 3 for simplicity, because my tables will be of a smaller size. We can even choose other, 2 actually can be chosen. It can be anything. It does not matter. If you end up in actually choosing b is equal to 1, so then we have only 2 digits, 0 and 1 are there, and this whole thing will degenerate to Cadmilia. In fact, you don't require in that case, this table will generate to Cadmilia, but of course, the distance metric is going to be different in Cadmilia and here. So once I explain Cadmilia, you will be able to appreciate that. But as of now, this can be anything. Okay. So number of rows in the routing table, we have to understand this. Number of rows will be equal to number of digits in the node ID. Okay. If there is a 4-bit, b is equal to 4 is chosen. So I'm actually using now a 4-bit hexadecimal digit for representing the node IDs. So how many hexadecimal digits can be there? 256 by 4. So those many will be there, and so you will end up in actually going to have those many rows which are going to be presented here. And now depending on if I'm going to use hexadecimal number, there will be 16 columns. If b is equal to 3, then there will be 8 columns. So number of columns will be always equal to 2 raised power b. So 2 raised power 4 is 16, so 16 columns will be there for a hexadecimal base 16 digits if they are going to be used for representing the pastry routing. So let's take an example. So here b is equal to 3, which has been taken, and this can now represent octal digits. Basically, the digits can be from 0 to 7. You are not allowed to have 8, 9, 10, and so on in the node ID. And I am going to take 4-digit node ID, which actually means 2 raised power 3 multiplied by 4. So 2 raised power 12, those many, that's a node ID space, which is still actually large. So let's take a node ID to 0256 first of all. So what the routing table will look like. So this will also explain how the routing table gets done. So the first column will be now derived by the first digit. So first digit I will take. So when the first digit is 0, this node itself can actually be put up here. So there is nothing else, only the same node entry will just remain here. Now first bit is 1, I will keep here, and I can choose anything which can match with 1xxx, which actually means 4xxx here. Take this example. If this particular cell is going to have this entry, this actually can have any node which matches with this. So 4123 matches, 400 matches. X actually means it can be anything. Okay, sorry, I should not have written this FFF here because I am talking about octal system. So let's call it 477. Okay, so there is no entry as of now. There is only one node. So I'm just leaving it as it is. So this actually means there is nothing. Then 2xxx, any entry which matches with this. So technically 2 raised power, there are 3 bits here, 3 here and 3 here, 9. 2 raised power 9 possibilities are existing. Any one of them can be placed here. Okay, but we are going to put a restriction on this, what can be placed here, because we want to have less amount of network resources to be consumed when doing peer-to-peer routing. Okay, we are going to have some kind of a proximity metric to decide which entry has to come in when there are multiple possibilities. Similarly, for 3, anything which is matching. So each one of these blocks can have an entry from 2 raised power 9, that much size block. So one of the 2 raised power 9, okay, entries is possible. So this block is representing 2 raised power 9 possibilities. Now come to the second column. So 0 remains as it is. Okay, So this will remain 0. I am now looking at the second digit. So second digit is 0, so this entry has to be maintained here, and then has to be XX. So 5 cannot come here. It has to be, can be anything. So 0, 2, 5, 6, I will be keeping here at 2 at this place, because 0, 2 matches with this. 0, 0 is not matching with this, so it is XX. So anybody which can come here. So this cell will be containing one entry out of possible 2 raised power 6 entries. So 3 bits here and 3 bits 2 raised power 6 possible entries. One of those will be coming here. 0, 1 XX and so on. Here 0, 2, it matches. So 0, 2, 5, 6, I will just put as it is. That's the closest. You have to be closest to yourself. Then 0, 3 XX, 0, 4 XX. So each one of them is representing a block of 2 raised power 6 size in the node ID space. So next entry, technically what I have done is I have actually taken this particular thing and I have expanded it in this whole row. Okay, 0, that's why it gets fixed everywhere in the highest order place. Okay, now on the second place is going to change 0, 1, 2. So wherever there is 2, I am repeating this entry. Now 0, 2 gets fixed here, and I am going to expand this into this third row. So 0, 2, 0 will come here. So I don't have any entry matching this. There will be total 8 entries which are possible, which can come here if they exist. Currently there is only one node, that's why these are all left out. So as I go along, you will actually appreciate this. So 0, 2, 1 X, similarly it goes on. Here 0, 2, 5, 6 actually comes in. So the same node will appear again. And as for doing the same way, I can only take 0, 2, 5, 0. Any entry which is in black, actually node does not exist. Okay, I am going to use the color to identify. But 0, 2, 5, 0, if it exists, will come here. Otherwise, there is no entry here. So all nodes which are differing only at the unit place, okay, lowest octal number place actually, digit place. So those will be all 8 numbers will be coming here. 0, 2, 5, 6 exists, so it is going to be present here. I have actually highlighted with the yellow here. So what pastry further did, because there were many possibilities, many nodes can exist actually which can come. There, this is representing directly a number, this is representing 8. One of the 8 will be coming. Here, one of the 2 raised power 6 will be coming. Here, one of the 2 raised power 9 will be coming. So when you have multiple choice, which one to pick up? So pastry actually innovated here, and they said we can choose when multiple options are there, and the choice will be based on the physical distance. Okay, how this physical distance has to be defined actually. So ideally, the communicating to this node which you are choosing should consume least resources of the internet. That's the idea. So yet the routing will become more efficient. It will become efficient routing compared to CORD, and this efficiency is actually much higher than CORD. So maybe if I want a faster routing, I can start choosing the options based on the what is our least round trip time. I can do a ping, and through the ping is a command which is used in any machine, can be used to find out what's the round trip time. The UDP packet goes all the way to the other side and comes back, and based on that you will figure out whether what's the time delay. Okay. So you just make the half of it after doing transmitting many packets, do the average and take half of that, and that will be your one side delay, and choose whichever is the least one. So this will actually make your routing very fast. So other options, not only RTT, you can choose geographical proximity. If you can identify from IP address longitude and latitude, you can do it on based on number of hops. You have to use in that case traceroute command to find out the number of hops. Now important thing for routing, only routing table and leaf set participates. Neighbor table never participates in the routing table. It's not supposed to actually. So if you have a hash ID being given to you, how the routing happens? Node ID will now search, look at the hash ID. Now hash ID, if it compares with the current node, it must be having some bits which will be present here. So some bits will be matching in the hash ID. So maybe these two are matching with this. The third one is not matching. This is different. So prefix match is only 2 digits in this case. So node ID will be from the routing table. It will search, it will choose such that it matches with hash ID with a longer prefix. So here it is matching 2 with the current node. So I need to choose an entry which matches with 3 or higher number of digits on the prefix side. Okay. So whatever your current is matching with the current one, it has to be longer. So for example, 2056 is the current node ID. 2426 is the hash ID. The routing table of 2056 contains 2421. So you can actually see with the current node, it's only matching with one digit. But with this entry, it is matching with 3, and this is the longest match. So you will hand over this query for this hash ID to 2421. So prefix match is now 3. It is not 1. If somehow you can't find a longer prefix, then for a hash ID, then it's actually already matching with you at some places. You can't find a longer prefix. Then you should choose a node ID which is having the same prefix match as what it is having with you, but it has to be numerically closer to the hash ID. Choose a node such that. Okay. Now, if you end up in finding out that you are the only guy who is the closest to the hash ID and there is no node which is having a longer prefix match, in that case, you have to just switch over to the leaf set based routing. Okay. So that's for the local optimality. So you do a faster routing, faster jumps with the routing table, and then when you reach very close to the root node, then you start using leaf sets. Okay. So of course, I have mentioned it here that you can only use leaf sets if you want, but that will be slower. So this routing tables make it very, very fast. And then what I have explained in the earlier slide, this same principle you can use it for routing the leaf set, any hash ID, once you are able to reach here. Now let's come to neighbor tables. What happens to the neighbor tables? So you will again choose L closest node based on the proximity matrix. So maybe number of hops or ping or maybe RTT. Based on that, you will choose the L closest one. So there is no node ID thing to be considered here. These are actually something which are very close to you. So if I am in IIT Kanpur and I will try to do it, I will end up in picking up all L nodes from IIT Kanpur inside only, because my round trip time to the outside will be larger. My hop count will also be larger when I go to outside world. Okay. So they will become kind of my proximity metric. So this essentially solves a big problem. It makes the things efficient. You will appreciate once we come to the process of choosing the nodes. So periodically you will request the neighbor table from all nodes which are there in your neighbor table. So when each one of your neighbor table, there are L such nodes which you have in your neighbor table. So they will give their entries to you. You get L square new entries. And now you will do a ping test if you are doing RTTP. If you are doing number of hops, you will do trace route to each one of them and find out the best L, and you will keep on updating them. So your neighbor table will always keep on updating. So in the beginning, for example, if I am only connected to somebody in US, so he gives his neighbor table, so I will pick up somebody who's closer to me. Okay. So the moment I find out somebody closer to me, either the entry is coming from the routing table or in my leaf set, the moment somebody comes close to me, I will just hop onto that. I will keep on replacing. And ultimately, I should converge onto a situation where all nodes in my neighbor table are in my close proximity. Okay, so under steady state, each node will maintain L closest node. Okay, this normally can be a separate function which can be plugged into the peer-to-peer libraries or middleware which you are using, and then the proximity can be used for doing the more efficient routing. So now each node periodically will fetch routing table and neighbor tables. So remember, it has to fetch routing table and neighbor tables from all the nodes which are present in its routing table and neighbor table. So whatever is there in your routing table and neighbor table, you will pick up each one of them and ask them to send you their routing and neighbor tables. So based on the entries which are going to arrive, you will update your own routing table entries, which are physically, as per the proximity are closer to you. So you may end up in getting, for example, a routing table here. So for this particular entry, you may get, say, 10 possibilities once the exchange happens. Once the 10 possibilities come, you will pick up one, the guy who is the closest to you, and put that here. So whenever you are doing routing to even to a longer domain, for example, this is a very long hop actually as far as the numeric distance is concerned, but the guy is physically closer to you. Okay. So all nodes will keep closer routing table entries and neighbor table entries. That's what happens. And a node will keep on moving to the entries which are better and better. Okay. And neighbor table makes it happen much faster. Routing table actually will very quickly they will try to find out. So for example, you are a new node. You are only able to build up your neighbor table. So you don't know in your routing table which is the closer one. What he is telling, maybe you got a far off node and he is giving his proximity based node possibilities to you. So you are not getting a closer nodes in your routing table. But when you get it, when you will ask your neighbor, neighbor will give his own routing table which is based on proximity. This is already optimized. When you give it, so somebody who is closer to your neighbor must also be closer to you than somebody who is arbitrary. So this actually leads to a much faster convergence because of that. So at this point, let me close this lecture, and in the next lecture we will look at an example for this pastry routing.